The gravitational constant was first introduced by Isaac Newton. I don't think that's a shock to anybody because sometimes that constant is called Newton's proportionality constant. He mentioned it in his publication in 1687, Philosophiae Naturalis Principia Mathematica, and I did completely slaughter that name, excuse my language ignorance. Now, it wasn't actually observed in an experiment, however, until 1798, and the first person who successfully measured it was an English physicist by the name of Henry Cavendish, who measured the very tiny force between the two lead masses by using a very sensitive torsion balance. Now, you should know that after Cavendish had found this, more and more accurate measurements were made throughout the years. So that's the history. Now let's actually use it. Okay, so Newton's law of universal gravitation states that, and I'm reading this, a particle attracts every other particle in the universe using a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. It kind of sounds like the Scarecrow from Wizard of Oz. Actually, go back and watch that. When you were a little kid, you thought that was really complicated. It's actually the Pythagorean theorem, but wrong. Anyway, that's just a side note. Let's talk about this in terms of the actual equation. So the force between the two universal bodies, planets, moons, etc., a large body. Actually, this applies to anybody. Anybody. It applies to anything. However, usually the force between smaller objects is so teeny tiny, we don't even notice it. It is inconsequential. So the force between these two bodies, of course, force is a vector. This is the magnitude of the force, and the direction of the force is going to always to be towards the other body or object. Now, when we're talking about the magnitude of this force, and all that means is if you have, let's say, the Earth and the moon, and you want to understand the pull of the moon on the Earth, that force is going to be towards the moon. But if you wanted to understand the pull of the Earth on the moon, that force is going to be towards the Earth. Of course, Newton's third law says those are going to be equal and opposite, which this proves as well. So when we take a look at the magnitude of this, we have this funky little constant that is called the universal gravitational constant. Universal gravitational constant. And we have the mass of body 1. You could say object 1. We're usually talking about planets, things that are really massive. And the mass of body 2. And then R represents the distance between their centers. Distance between centers, just to give you an idea of what this equation means. So basically, when you look at this equation, you see, okay, no matter what happens, the gravitational constant's not going to change. The masses of the planets or the moons, etc., are not going to be changing. However, it relates the distance between them. So if the distance doubles, that force is going to be 1/4 of the size. So let's go back and just take a look at this equation. Let's just consider the magnitude. Now G, the approximate value of G is 6.67 times 10 to the negative 11 meters meters cubed times kilogram divided by, wow, Shay, meters cubed over kilograms seconds squared. So let's go ahead and take a look at a problem that uses this. As my son would say, this is not rocket surgery, okay? Now, it really is, and I hate to say it, plug and chug. It really is. But a lot of my students get very confused when there are no numbers. They're like, Miss First, there are no numbers. What do we do? Well, let's just take a look at this. Now, we know that r represents the distance between the two objects. Well, if r we just start in the beginning, the two objects are in their original position, okay, they're in their original position, then the force between them is going to be equal to that gravitational constant, m1 times m2 over r squared. We're going to have r be the original distance. Now, let's say that that distance increases by 3. Well, now that new distance is not going to be r, it's going to be 3r. And if it is 3r, don't forget you have to square that coefficient as well. If it's going to be 3r, oops, I don't know where that came from. That just snuck in my mind somewhere. Okay, it's going to look like that. And in order to compare the original force and this force, all we have to do is identify, see if we can find this term. Well, in this case, that is pretty easy, because here we're just going to pull out the 1/9, and we can see that the force is simply going to be 1/9 of the original. Don't make it more complicated than it is. All right, I'll see you next time. Make it a great day.